So we're going to start with a very, very fast safe network overview since Doug already covered most of the ground, mostly going from what you just heard right now down to where PARSEC fits. So we're going to speak about why we need consensus and what we need from a consensus algorithm, and then why we had to do our own, which is PARSEC. Then most of the talk is going to be a deep dive explaining exactly how PARSEC works. Then a little bit about malice, but we may not have time to cover that, which is just kind of a side note. And then finally a little status update on where we are in the process. So I'll hand over to Bart for the safe network overview.
So basically Doug already showed you a better diagram than we have, but the main structure is that we have crust on the lowest layer, which handles the network connection. Then we have routing on a bit higher level, which provides the structure to the network, basically divides it into sections and provides consensus, provides some protection about Sybil attacks, things like that. And on those we have two main things built. One are vaults, which are the nodes that are hosting data on the network, and the other ones are clients, which is basically a basis for all the apps that you can build that are able to work on the safe network. We are on the routing team, and basically this division into layers is what allows us in routing to focus on problems at a very abstract level. So basically what we are doing is mostly math with some practical applications, but it's a large part of math, which is kind of nice if you look at it the right way. Okay, so what is routing about? So first I said it partitions the network into sections. So basically we divide the network into some subsets of nodes. They are disjoint, we call them sections, and every section is basically a unit of consensus first. So basically it's the smallest unit that makes collective decisions, and then sections communicate between themselves to exchange data and things like that. There is also a notion of closed groups. We have a notion of distance between nodes. I won't dive into details here, but the point is that we have some notion of a distance between, for example, a node and a piece of data, and every piece of data is stored on a few nodes that are the closest to it in this address space. So this is also a task for routing. Mitigate Sybil attacks. So this is also what Doug touched upon: node aging, node relocation, like mechanisms like that. Secure communications across sections. So basically we want to, if we receive a message from a section, no section knows about the whole network. It only knows its immediate neighborhood. So when we receive a message that is claiming to be from a section that we don't know about, we want to have a means of verifying that it is indeed sent by this faraway section. So this is also something that routing does, and enables consensus within a section. So we'll go into a bit more detail on that in a moment. So yeah, basically why do we even need something called consensus in a section? So we want nodes in a section can observe some events in the network happening, like node requesting to join a section, node dropping from a section, like some, I don't know, passing data around, etc., etc. So for various reasons, we need to agree about the order in which those events happened. Why? For example, the classical example is the problem of double spending. So for example, once we have cryptocurrency on the network, we want to make sure that no actor can spend the same money twice. So send it both to, I don't know, to Alice and both to Bob. And we want to only validate one of those transactions and not the other one. So in order to do that, we need to know which transaction happens first, and all nodes in the network need to agree about this order. So this is where the consensus problem comes in. And this is actually what is known in the literature as the Byzantine generals problem. So I'll let Pierre take a deeper dive.
So the Byzantine general problem is, I'm pretty sure you all know, kind of a well-known problem in math. It's kind of famous for blockchain being one of the solutions to it in some sense. It was formulated in 1982 by Leslie Lamport as kind of a metaphor of generals wanting to attack a city, and then some of the generals are dishonest and trying to confuse the other generals into attacking at different times so that they get exterminated. So that's kind of like And then the objective is to design an algorithm that, despite some generals being dishonest, lets honest generals agree on when to attack the city. So it sounds simple when you just put it in this kind of example way, but it's more complicated than it seems. Like there have been decades of research into it, and we're not even at an optimal solution where everyone can say, let's just use this, it's got all the properties everyone needs. So there have been many, many solutions, and each of them has some trade-offs, and so we're still navigating this space. So because we ended up needing consensus for the safe network, we looked, of course, at what we could use from the existing literature, because if we could just pick a plug-and-play solution, then we wouldn't spend time creating our own. And so before doing that, we had to define our needs from a consensus protocol. So ideally, we need something asynchronous, because we're speaking about network latency in an internet-type application. So basically, you don't know anything about the speed at which a message will reach someone else. You can have you can think of DDoS, these kind of problems. So it's really hard if you start baking synchrony assumptions. You're probably not going to be resilient at the scale of an internet-type network. We need scalability, because our ambition is to connect all the computers in the world and to deal with all the data in the world. We need for it to work in a permissionless setting, related to the reason why we need an asynchronous network. You can't trust people's computers, because you know that some people are going to try to disrupt the network for some or other reasons. Also, another point with permissionless is that nodes, computers from people are not reliable. They go offline and online all the time. So your network needs to be resilient to that too. We need for the process to be open source, because the safe network stands for secure access for everyone. And that also means that everyone must be able to audit the code. Like, there is no trust in a single entity. It's decentralized, it's for everyone, it's reviewable by everyone as well. And finally, we need it to be simple, partly because we're math snobs, and partly because simple is a key feature of security. If it's simple, everyone in the field can review it and can actually say, yes, it's correct, or no, it's not correct. If it's complicated, there are traps that could just bite you 20 years later when the network is used by everyone, and then you've got a problem. So keeping in mind that this is our target for everything, let's look at what exists in the literature. One you may be familiar with is the blockchain. So it's kind of a solution to consensus. It's not asynchronous, that's more or less debatable. It's definitely not theoretically asynchronous. It's not even weakly synchronous. But in practice, you could say it's got some asynchrony-ish behavior. But the biggest problem with blockchain is that it wouldn't scale to a network that stores everyone's data on the internet. You couldn't, like in a blockchain, you have to download the ledger to everyone's computer, and that's already hundreds of gigs for dealing with money transactions. So if you try to deal with all the data on the internet, that would definitely not scale. So from the very beginning, we knew that blockchain was not the solution for our particular use case. There is one recent development in ABFT called Hashgraph, which is actually a pretty nice solution. They claim to be asynchronous, and that's debatable. They have some flaw in their proofs. But the main problem is not that with Hashgraph. The main problem is it's not open source. So if we wanted to, say, give them a royalty fee and use it in our network and license it to our users, then we would have to give a binary blob of code to our users, and that goes deeply against our ethos. So Hashgraph for us is not an option. And competition to Hashgraph that's open source and that's also pretty cool is Honeybadger. So this one it's got two problems. one is it's not extremely simple because it has to deal with complex cryptographic primitives like threshold encryption for a part of the algorithm that's called the command coin. But if it was just that, we could also maybe close an eye. The main problem is that also related to the command coin, which is a subset of it, it cannot be at the same time asynchronous and permissionless. Because when you add a node to the network, which if you're permissionless, nodes will drop out and so you'll have to replace them, then you have a synchrony step currently in Honeybadger. So for that reason, we couldn't use it. So one last example, because I'm not going to list all the Byzantine fault-tolerant solutions out there, but Avalanche came out the same week as PARSEC, and we would have possibly considered collaborating with them if it solved all the problems we need, but it's a synchronous BFT solution, so didn't work for us either. So altogether, we just had a deep look at everything that's out there. We saw good ideas, bad ideas, but mostly we saw that nothing had exactly the properties we need for the safe network. So that's why we ended up doing our own, and Bart is going to start with this.
So yeah, so basically what we came up with is PARSEC, and how is PARSEC presenting itself on this background, on the background of the other algorithms? Well, okay, so its features. It's almost asynchronous. Well, we intended it to be fully asynchronous. Basically, in the last moment, we discovered a small flaw. It's not that big of a problem. We expect it to have pretty much no impact on in practical uses. We will actually talk about it a bit more deeply. But yeah, for all practical purposes, it will usually work even in a purely asynchronous setting, which is nice. It is scalable. So basically, what do we mean by scalable? It has nice message complexity. So in order to reach consensus, we need n log n messages as opposed to, I don't know, n squared and n cubed even sometimes for some algorithms. It can work in a permissionless setting. Permissionless, it's not really an adjective we can apply to the algorithm itself, but there is nothing inherent in the algorithm that would prevent us to add or remove nodes on the fly, which is also one of our requirements, as Pierre mentioned. It is fully open source. Well, we created it, we decided what license it should be on, so it is GPL v3 with linking exception, and basically everything about it is open. We are open to contributions, we are open to constructive critique. Basically, it's everything the same as the rest of the safe project. And it is simple, and by simple we mean it is pretty much as simple as you can get with an asynchronous Byzantine fault-tolerant algorithm, which might not look that simple at the first glance, but still it is composed on pretty self-contained building blocks, each of which is kind of understandable on its own, and they compose together into a bigger algorithm. As also Pierre said, it provides better security because, well, you can audit every block separately. You can say this is correct, this is not correct, and basically you know what you are standing on. Yeah, so I'll let Pierre do a quick, not in a nutshell,